Good morning, everyone. Good morning. Shall we begin the session, everyone? Yeah, today's topic is the logic gates. In the last class, we have finished with the earlier topics. And today's topic is the logic gates. Logic gates are the switching circuits that perform certain simple operations on the binary number. Whatever the binary number we are using, so whatever the simple operation that is performed, so they are performed on a binary signals, and these operations are chosen to facilitate the implementation of a useful function. Now, let's come to the first function, that is a AND function or the AND logic gate.
So first gate is a AND gate. Yes, and AND gate is used to identify what are the various inputs and how these inputs are combined to make the circuitry. The AND gate logic operation. Now this is the AND gate truth table. What is the truth table? That is a combination of the zeros and the 1 and the AB. There are two fields, then 0 0, and what is the result? That is a 0. Because if both the inputs are 0, then the output is also 0. Then 0 1, if one of the input is 0, then again the output is also 0, and again 1 0. In this case also b is negative, that is a 0, so again the output is 0. Then 1 1, this becomes 1. Why? Because both the inputs are 1, so that is a 1. So 1 1 is 1. This is AB, then function of A and B. Now this is a symbolical representation, how we can represent the AND gate. So A and B are the variables, and note the use of the dot operator to denote the AND. That means we are using A into B. That is F equals to A into B, and A and B are connected with the logic gate. So this is AB or the A into B. Now AB are the variables and note the use of the dot operators. To denote the AND operators. These are the various examples that determines the output waveform when the input waveform A and B are applied. So we have applied the input waveform, and this can be applied to the, or this can be given to the output waveform. Now next one is the OR gate. So one is the AND, that is over. Then next one is the OR gate. So this is true when both the inputs and the outputs are closed. Now this is a table. In this case, yes, output is only 0 when both the inputs are 0. Otherwise, if one of the input is true, that is 1, the output is true. In this case, first one is 0 0, both the inputs are 0, then it becomes 0. Then 0 1, it becomes 1. Then 1 0, it becomes 1. Then 1 1, it becomes 1. So this is 0 0 0, 0 1 0 1, 1 0 1, 1 1 1. This is a symbolic representation of this one. Then this is F or B, sorry, A or B. Then this is a symbolical representation or the graphical representation. One is a AND gate, this is the OR gate. And these are the variable, and not the use of the plus operator to denote the OR. The next is NOT truth table. That means complement. 0 becomes 1 and the 1 becomes 0. This is the graphical representation of the NOT gate. There is a A dash, that means we are using the bar over the A to denote the NOT. And sometimes a bubble is used to indicate the inversion. Inversion in the sense, what are the various tools that will be available to invert the things, that means change the things. And in fact, it is simpler to manufacture the combination NOT and NOT OR than it will deal with the AND and the OR. And NOT AND becomes NAND and NOT OR becomes NOR. This is the NAND and the NOR. Then this is the truth table for the NAND. This is A NAND B. This is 0 0 1, 0 1 1, 1 0 1, and 1 1 0. Then NAND gate, this is the A into B. Then after this, yes, after making the AND gate, we are converting things, that is a NOT of AND. Then NOR gate, this is the A NOR B, 0 0 1, 0 1 0, 1 0 0, 1 1 0. Then AB, A plus B AND. Now this is the XOR gate. This is A plus B, and there is a curve shape that is also available with the OR gate. This is the A or XOR B. This is the exclusive NOR truth table, that is a NOT of the A XOR B. Then exclusive NOR gate, this is the A plus B, and this is known as the equivalence gate. And then rules and laws of the Boolean algebra. These are defined by the rules and the laws, and the most significant which are represented over here. This is the commutative law. This is A into B equals to B into A plus B equals to B plus A. The next one is the associative law. This is A into B into C equals to A into B into C. Then A plus B plus C, this is one bracket, then in the another bracket, this is the same, this is A plus B plus C. And this state that the grouping of the variable is unimportant over here. And distributive law means bracket is distributed to the variable. This is A into B plus A into C. This states that when we remove or when we can remove the parentheses by multiplying through, and these are the same as in ordinary algebra where plus and the dot are the interpreted as addition and the multiplication. Now, what are the various basic rules involving one variable? So A plus 0 equals to A into 0 equals to 0. Then A plus 1 equals to 1 and A into 1 equals to A. Again, it is A plus A into A. A plus A dash equals to 1, A plus A dash equals to 0. It should be noted that A into A or the A double A equals to A. That means A complement or A complement is A. Then what are the various rules that is available or rules and laws of the Boolean algebra? So this is the informal proof of each of these rules that is easily accomplished by taking the advantage of the fact that the variable can have only two possible values. For example, rule 2, this is A plus 1, that is 1. Then if A equals to 0, then 0 plus 1 is 1. So this is A plus 1 equals to A. Now 0 plus 1 is 0. And if A equals to 1, then 1 plus 1 is again 1. Then these are the useful theorems. That may be associative, that may be commutative. So this is A plus A into B equals to A plus A into B equals to A plus B. And these may be proved in a similar manner also. For example, this we are taking the two variables, one is 0, 0, then 0, 1, 1, 0, and 1, 1. Then A dash B, then A plus A dash B. So this is A dash into B, then A plus A dash into B, then A plus B. So these are the defined rules. This is available with the or same as the A plus A dash B. Now next rule is A plus 1 equals to 1. That is the informal rule that we define with the Boolean algebra. Yeah, this can also be represented with the use of the two variable. There are two possible values. For example, rule 2, then A plus 1 equals to 1. Finally, we come to the DeMorgan's law, which are particularly useful when dealing with NAND and NOR gate. Whatever the NAND gate, whatever the NOR gate that we are dealing with, then what are the various rules and the laws of the Boolean algebra. So we finally come to the DeMorgan's law. And they are stated as follows. This is A plus B equals to A complement into B complement. This is not of A or B, not of A and the not of B. Then A nor B, this is not of A and A not of B. Then it is relate with the not or and it can be extended to any number of the variable. This is a plus b plus c. This is a into b into c. Then a plus b equals to a dash into b dash. This is DeMorgan's theorem 1 because plus is converted into the multiply. Now look over here. This is the sentence. Why? Because a plus b you know. Now the complement, that means 0 becomes 1 and 0 becomes 1 and the 1 becomes 0. Then a complement and again 1 1 0 0. Then again b complement 1 0 1 0. Then a complement into b complement, that means 1 1 becomes 1, 1 0 becomes 0, then 0, then 0. So this is 1 0 0 0. That's similar to the a plus b complement. This is DeMorgan's law number 2. That means multiply is converted into the addition. This is a complement into b complement, that is, or a into b whole complement equals to a complement plus b complement. Now this is a into b 0 0 1 0 0 1 0 0 1 1 1. Now a into b whole complement, this is 1 1 1 0. Then a complement 1 1 0 0. Then b complement 1 0 1 0. Then a complement plus b complement. This is 1 1 1 0. Now these are again the rules, that is a plus b whole complement equals to a complement into b complement. Now let a is I won the lotto, let b is I am happy. The first DeMorgan's theorem law tells us that note I won the lotto or in I am happy the same as a note I won the lotto and on. This is a DeMorgan's theorem. This is a plus b whole complement, a complement, b complement. And taking the NAND gate as an example, we can derive effective AND or gating, although physically we are using only one type of gate. For example, f equals to a into b plus c into d. This is a into b whole complement, c into d whole complement. Now, this will be referred as a NAND or NAND gating, and any logical sequence that may be implemented using the NAND gates only, and this may be regarded as a universal gates, and same is true for the NOT gates. And the other advantages of using the NAND or the NOR gates are simplest and the cheapest to fabricate, then fastest operating system, then lowest power dissipation. And this is a simplification of the expressions using the Boolean algebra, and it is also important to minimize Boolean functions, as this often brings about a reduction in the number of gates or input that are needed. For example, consider this is AB plus A, B plus C plus B, B plus C. This is a simplification of the expressions using the Boolean algebra. This is considered, and in general, multiply out and collect the common terms exactly as you would do when simplifying ordinary algebraic expressions. This is the expression of the problems using the Boolean algebra, and most real problems are defined using a centennial structure, and it is therefore necessary to translate such sentences into Boolean equations if we are to derive a digital circuit to give a Boolean result. For example, it will snow if it is cloudy and it is cold. If and the and divide the sentence into different phrases. Now let f will be the it will snow, that is 1 if true, 0 if false. A is if it is cloudy equals to 1 if it's true, 0 if false. It is cold, then 1 if true, 0 if false. So F equals to A into B. This is for the cloud detector and the cold detector. Now the next topic is, yes, correct. Corresponding digital circuits. So this is for the A and B. Means two AND gate is converted into one OR gate. So two AND gates are going into AND gate is converted into OR gate. That means two AND gates are converted into the one OR gate. And the expression of the problem that is used with the Boolean algebra. And for more and more complicated problems, we define the problems by constructing a truth table, and we will introduce the idea for the simple example and can go on use it in a more complicated example. Now, if we have a problem or the Boolean expression with four variables, then our truth table would like this with the four examples, or with the four variable for input. There are A, B, C, D, that is 0, 0, 0, 0, 0, 0, 0, 1 and 0, 0, 1, 0. That means in the first line there are total 8 zeros and the 8 ones. Then in the B there are 4 zeros and the 4 ones, 4, 0, 4, 1. Then in the C there are 2 zeros, 2 ones, 2 zeros, 2 ones. And in the D there is 0, 1, 0, 1, 0, 1, 0, 1. Then each combination of the logical variables A, B, and C makes a 4-bit binary number in the range 0 to 15. Let's number each row with the equivalent decimal numbers. And this is the expression of the problem using the Boolean algebra. This is row 1. Sorry, row is starting with a 0. So we have total 16 rows. So that starts with a 0 and ends with a 15. So there is a row 0 till 15, and there are total 4 columns that is available over here. Then expression of the problems using the Boolean algebra. This would use at the equivalent Boolean expression. For example, 0, 0, 1, 0 is equivalent to the A, B, C, D. And A, B, D are the NOT gates. Then the expression of the problem with Boolean algebra. There is a row that starts with a 0 and ends with the 4. So this is from the 0 to the, it starts with 0 and ends with the 15. So this is from 0 to 15. Then we call each of these product terms as a min term, and note that each min term contains each input variable in turn, and we can express any Boolean expression in the min term form. If f is expressed this way, we say it is in the sum of the product form, or it's a first canonical form. Then expression of the problems using the Boolean algebra. This is A, B, C, D are the four variables, then A dash, B dash, C dash, and D dash. And the min term is M0, M1, M2, M3 till M15. Then the expression of the problems using the Boolean algebra. This is, for example, in the case of the alarm circuit, we have A, this is the alarm switch is on, then B, the door switch is open, then C, it is after 6 p.m., then D, the window switch is open. F equals to 1 equals to, if A equals to 1, B equals to 1, C equals to 1, then D equals to 1. And this is the alarm time that will ring if F equals to 1. Then F equals to M3, M7, M11, M12, M13, 14, and why? Because M3 are the min term expression when both the C and the D are the ones. And these are the min term, that is M12, M13, M14, when both A and B are the 1. And the alarm should ring if any of these expressions occur, that is if F equals to AB plus CD. And these are the various expressions that denotes with or that starts with a 0 and ends with a 50. Then the dilemma and the digital doctor, that is represented by the D shape for long Department of the Electronics and the Electrical Engineering. In the cast, this is the director of the public health system, this is the doctor logic. And the scenario is overcrowded public health clinic with many obviously ailing clients that are looking for a diagnosis. Now there are 6 2 inputs, 2 3 inputs, 1 4 input, 9 gates, and that's all. The power supply if, switches if, then LED if, box if. Well, I will just have to see if it can make it work then with that. And there are 4 categories of this, and there are 4 symptoms, that is the chills, rash, bloodshot eyes, and the fever. And there are 2 elements, that means there are 2 parts or the 2 outputs. One is a Boolean virus, one is a digital field. And will the computer scientist be successful? Will the director have to spend for the National Guard to control the binoculars and growing crowd looking for the diagnostics? Stay tuned. And there are 4 symptoms, this we have done. And anybody who don't have or who got any of these symptoms will have either Boolean virus or the digital field. And if there is a chill and a rash only, then it is a digital flu again. That is a chill by itself or a chill or any other combination of the rash. Then bloodshot eyes and the fever, or they have got the virus. What are the various available equipment? There's a 6 input 9 gates, 2 3 input 9 gates, then 1 4 input 9 gates. And the director's dilemma key facts, there are 14 symptoms, again it is using. And there's a chill and the rash only, then it is a digital flu again. Then this is a simplification using the min terms and the k maps, Karnoff maps. This is t equals to 0, t equals to 1, and again t equals to 0. Then this is a simplification using the mid terms and the k maps. So this is used to identify the group of the adjacent ones in the Karnoff map. And note that the two squares are the adjacent if they share a boundary, and this includes the top at the bottom edges and the left at the right edges. And this will use to identify the least number of the variables that are required. And the simplest expression is in the logical order of the min terms. And the simplest